Welcome everybody. This week we have Gabriele Benedetti, who will tell us about rigidity and flexibility of periodic Hamiltonian flows.
Thank you very much for the invitation. It's great to be here and to be kind of first speaker of this Italian spin-off of the of the Symplectic seminar. So today I want to talk about a story which is starts in the 19th century, but is today still very active because of a connection with systolic geometry. It's about how to construct Hamiltonian flows which are periodic, and how to do so in a kind of class of flows that is kind of meaningful, has some physical interpretation. And we will see that basically we will have both some rigidity phenomena and flexibility. So my main theorem today will be on the flexibility side, but I will also kind of try to give you a flavor of the rigidity in this story. So then the problem here is like how to construct such flows in a given class, and then in class of examples, let me say immediately what are the kind of examples that we want to consider. The first one is the one coming from the 19th century in the work of Bertrand. These are the central force potentials. Central force potentials. Okay, this is a very simple setting. In R2, you take a particle subject to the conservative central force. So it's something like this. U is a particle in R2, and then U is just a potential. Okay, this is the first class of examples that we are going to consider. The second class will be geodesic flows. For this, we just take closed manifold, closed Riemannian manifold. Then we have the geodesic equation. Acceleration equal to 0. And then the one that I'm most interested in are the magnetic geodesics. I will try it here. Where now we also put a Lorentz force to our geodesics. So these are magnetic geodesics. We add to our picture sigma a closed two form. Close to form on Q, and then we are looking at acceleration of the particle equal to the Lorentz force, or Q dot, where Y, the Lorentz force, is, I can write here, it's an endomorphism of the tangent bundle, which is given by pairing sigma and G. Also, if you take sigma, and then G, and insert Y inside, is how you get your Lorentz force. Okay, and this is, like in the market, this is still a Hamiltonian flow, so this is maybe more well known for Riemannian manifold, for standard geodesics, but it's also Symplectic, Hamiltonian flow. In this case, you have the twisted symplectic form on the tangent bundle. So d wedge dq, and then you need to subtract the pullback of sigma. All right, and the Hamiltonian is still the standard in etiquette. All right, so if you want to have a kind of a geometric interpretation, which is also good for the examples that come from our talks, you can think of Q being of dimension 2. Most of our examples would be anyway low dimensional. In this case, your sigma is just a function times the area form. And now your equation up there, this is equivalent to saying that you have an orbit with energy h, so 1/2 q dot square equal to h, and that the geodesic curvature with respect to g of your curve q is equal to the function f of q divided by the speed of the particle, so square root of 2h. Okay, so in dimension 2, these are basically the curves of prescribed geodesic curvature. And the prescription is given by a function f, which can be anything really. So this makes also a connection with the study of hypersurfaces of prescribed mean curvature. This is like a topic which is very big, and this is just the kind of the case, the kind of the baby case where you are looking at just surfaces and curves. Okay, so these are the examples that we want to consider, and then let me be a bit more precise what I mean by periodic Hamiltonian flow. So here, what I mean is actually a very specific example or condition called the Zoll condition. Are there any questions so far about the definition or the examples? All right. So what I want to look now, I take M omega symplectic manifold, and I consider H Hamiltonian function, and I call, so we say that a level set sigma of this Hamiltonian function is Zoll, or that the system is Zoll at level H. If the Hamiltonian flow yields free S1 action on sigma. Up to time reparameterization. Okay, so we are kind of looking now at Hamiltonian flows which are autonomous, so that my function h does not depend on time, and I'm looking at energies for which all orbits are periodic in a bit quite stronger sense that the action of the Hamiltonian flow is actually a free S1 action. So all orbits, basically, you can think they are foliating and giving you the structure of an S1 bundle. So something like this. So to identify these two things, this will give you kind of a Zoll situation. What you don't want is the so-called best situation, where instead you have some orbits which are shorter than others. So it's a kind of exceptional ones. And then you have other orbits which are still periodic but kind of wind around. It would be not Zoll situation. Okay, and there's also a lot of research on this recently. I think we will have Marco. I think I don't know what he speaks about, but also, for instance, Mazzucchelli, he worked a lot with collaborators on this more general best case. All right, so this is kind of the framework, and then in our class of examples, we have a lot of these Zoll flows, which were classically known. And now the idea of the talk is to explore how much of these examples are kind of the only examples that you can find, or maybe you can have other kind of more flexible constructions. No? So the classical examples, you have the Kepler and harmonic oscillator potential. Oscillator potential. So this is the case UR equal to minus K over R, or UR squared, positive number, or you have geodesic flow on S2 for RP2, with G, the standard round metric, as well as the constant curvature metric. And then you have the magnetic flow. Let's see, the one that is most interesting for us is on the two-torus. G flat. And sigma just the multiple of the area form, let's say multiple 1. Okay, so in this case, you have that your curves are just circles of a given radius, which depends on the speed. Okay, already here there is some kind of flexibility, rigidity phenomena, in the sense that if you look just on surfaces, these are the only two surfaces admitting geodesic Zoll flow, while here basically you can do the same construction on every surface. You would find something similar if you put here a metric of constant Gaussian curvature. Okay, so these are kind of the examples which were kind of classically known, and then already in the 19th century there were the first papers to try to understand how much this can be generalized. So let me start introducing the rigidity results. But first I want to make a comment of why do we care nowadays. So this is an old problem, but actually nowadays we care about this because of relationship with systolic inequalities. So let me do this first. Why do we care?
Can I just ask a question?
Yes.
Aren't there examples of geodesic flows on S2 that are not the standard one?
Yes, yes, yeah. This would be on the flexible side. We will see that, for instance, in this, I can really make this comment. For these two manifolds, we will see that on this manifold there is rigidity, while on this manifold there is flexibility. So you will find huge deformation on this S2 by Zoll metrics, indeed.
Sorry, your comment was that for constant curvature, those are the only S2.
Yeah. So these are, I mean, these were the ones that are classically known, let's say, and then this we will discuss examples of how to construct other examples or situation where you cannot construct other examples of these things. Yeah. Okay. Are there other questions before I go to the motivation? Okay, so why do we care? So here, I want to talk briefly about the local systolic inequalities. What is the idea is that if I now take, assume that I have my sigma energy surface of contact type. So then this means that there exists some alpha contact form. And sigma, and the red flow of alpha is equal to the Hamiltonian flow of the Hamiltonian. H. So now what you can do, basically, now having the red flow of alpha, you can define the systolic ratio. The systolic ratio, rho of alpha. This is by looking at the period of the minimal period of a periodic orbit, and you normalize by the contact volume of sigma with respect to alpha. Okay, so this is the number which is 0 to infinity, would be infinity if you find a contract sample to the Weissman conjecture. And the local systolic inequality tells you that Zoll Zoll contact hypersurfaces are exactly kind of optimal if you look at this this quantity. So it tells you that it's kind of local systolic inequality. Tells you that if sigma is Zoll and sigma tilde is nearby sigma, another compact hypersurface, then the systolic ratio of alpha tilde is less or equal than the systolic ratio of alpha. And equality holds if and only if alpha sigma tilde is also Zoll. Okay, so locally, basically what this is saying is that Zoll hypersurfaces are really the local maximizers of the systolic ratio, and global, this is not true. There are examples by ABHS, Abondandolo, Brahma, Rinevich, and Salomao. And actually also this theorem has now many contributors. I must say that in this kind of context was brought by Spiva and Balashev for the first time, which proved a weaker version having some non-degeneracy. And then ABHS did the case basically when sigma is the standard trisphere. And then I did with Jiangsu Kang the case where dimension of sigma is 3 general, and with Alberto then we did the case in any dimension, so this is Abondandolo. Okay, so this is kind of the motivation. Motivation from this question comes also from the Viterbo conjecture. So you can also think of this in the this quantity here as a capacity in certain cases. For instance, when you have a convex hypersurface in R2n, and then you can ask similar questions about bounds on the capacity in terms of the volume. These are a big set of questions. I think Alberto will speak exactly about this problem in 3 weeks or so. Yeah. Okay, so this is why we care about this stuff. Okay, then let me now go to the rigidity side of the question, and then I'll explain some of the recent results about flexibility. Okay, so the rigidity. Results. So in the case of central forces, this is due to Bertrand, 1873. He showed that if U is a potential which is somewhere attractive, potential. So somewhere attractive just means that just means that somewhere this u prime of r is positive. No? Also, that the force that for some radius is pointing inside. No? Otherwise, if you have a repulsive force, then you don't expect to find surely Zoll things. So it is somewhere attractive potential, such that with the property. The property that all bounded orbits are periodic. Then you are in one of these two cases above. Then U is either Kepler or harmonic oscillator. So in some sense, it's saying to us that you are not only just looking at one energy, you're basically looking at all energy. So you're requiring something which is actually stronger than kind of having this Zoll condition at one energy. You say if you know that all bounded orbits are periodic, then these are the only two cases possible, the Kepler and the harmonic oscillator. Also, the catch is that if you ask periodicity for many energy levels, then you have a very restrictive answer. Okay, so this is the first type of rigidity, and then you have another type of rigidity coming from topology. This is the case of RP2. So this is the theorem of Green 90 years later. That shows that if G on RP2 is Zoll, then G has constant curvature. Here, in some sense, the energy business is not relevant anymore since they are all kind of conjugated in all energy levels. No? So asking for one energy or all energy is the same thing, but kind of this rigidity you can think comes from topology. And the last rigidity result is about magnetic flows. And this we proved with Luca, Asselle a couple of years ago, and tells you the following thing. So let Q be a magnetable surface. And suppose now you take a magnetic two form, which is not identically zero. So sigma not identically zero. So you have a genuinely good magnetic field, not identically zero. Now, if I know if all, or let's say, if there exists H0 bigger than 0, such that for all energy levels below this threshold, so the threshold 0 at 0, all magnetic geodesics with energy H are periodic, then you are in the very specific case. So then G is constant curvature, and sigma is just a multiple of the area. Okay, so this is again maybe more similar in spirit to the Bertrand rigidity result. So that if you have periodicity for an open set of energies, and in this case you want this set of energy to be close to 0, then actually you have very few cases, just the example that we were discussing before. Okay, so here there are a lot of open questions. If it's possible to cook up an example where you have an open set of energies such that you are periodic, but maybe this set is not including zero in the closure. So there are many things that one can try to explore. No, but this is so far first result, and there are also some other results. Maybe if you assume some integrability of the flow. Yeah, but this I just present this as an example. All right, so these are kind of the rigidity results that I want to present, and now I want to kind of zoom in on the flexibility. There are two things that are kind of left from the example from before. The one that was mentioned by Vinicius, the case of geodesic flows on S2, and the other case that one can now try to tackle is the case where you have a magnetic flow, but you're just required to beat Zoll at a single energy level. No, not that many. These are the two examples I want to discuss. The example of Bertrand is also interesting to see if one can weaken this to get some flexibility, but also, yeah, we don't know. Maybe it's a nice research project. All right, I can erase here. Is there any question on this rigidity part? Okay. Then let me go to the flexibility. Results. So, and let me start with geodesic.
Sorry, can I ask another question?
Yes.
Is the other direction true for any genus? Like, can you find, if you take a constant curvature and you take this sigma on any surface, you get Zoll?
Yes, that is true. Yes, if you take constant curvature and sigma is the area form, then you get Zoll, but you need to specify also which energy you're taking. So in the case of S2 or the torus, then you will have it for all energies. But if you go to higher genus, you will have this property only up to the magnetic-critical value of the universal cover. So there is a certain threshold where you then lose this Zoll property, but it's an interval exactly of this type, from 0 to some.
Okay. This H0 is the magnetic critical value?
Yes, so in the specific example will be the magnetic critical value. And here actually we just need any interval, any small interval. And actually, I mean, the proof is like finding kind of a normal form for the Hamiltonian vector field where you really see both the curvature of the metric and basically the sigma, and arguing that if these are non-constant, then the flow cannot be Zoll. Yeah. Other things. Okay. So then the flexibility result. The first side of the story is the geodesic flows on S2. So what is the setting here? So this theorem. Take U to be a function on S2. Then you have an equivalence between two things. There exists deformation G tau, which is conformal with respect to the standard metric, which is Zoll, and also with same volume. So the volume does not change. It's just a normalization for all tau in some interval minus delta delta. So you are kind of deforming your constant curvature metric by conformal metric, where this U is basically your tangent vector at 0. No? But you have now a full path in some in some interval, and then you're saying that this path here is made of Zoll matrix for all tau, and this is now an if and only if. If and only if, I put it here, U is odd. Okay, which on
Is what?
odd. Sorry, yeah, yes. Up there. Okay, so this happens if and only if U is odd function on the sphere, which means that on antipodal points takes opposite values. Okay, so you find this path if and only if the function U is odd. And there is kind of one easy direction. So maybe let me write it too, which is this direction here. This is due to Funk in 1913. And this one here is the hard one. This is due to Guillemin in 1976. Now, because now you need to, for each U, you need to construct really the Zoll deformation. And this is a kind of a proof that now we will see how we take the idea of this proof and we will have a similar argument in the case of magnetic flows. And this is a kind of implicit function theorem proof. So implicit function theorem proof. All right. So also this maybe tells you why, or it's a nice kind of relationship with this rigidity result. Now, since your function U is odd, you see all these deformations are very far away from being deformations of metrics that can land on RP2, where you would expect instead a function U to be even in order to have a deformation which is good in RP2. So in some sense, it's kind of orthogonal to the deformations of metrics which come from RP2. All right, so what we want to do now, we want to explore a similar result, but for magnetic fluids. Okay, while I erase, I can make also another comment. Actually, if you require your metric to be of a revolution, so this is result is due to Zoll. That's why we name Zoll matrix. Here, mark is an explicit construction. For metrics of revolution due to Zoll. Zoll in 1903. That seems strange that all most of the results were proven in years ending with the number 3. Okay, okay, so this kind of really explicit construction, while this theorem by Guillemin is an implicit function theorem, so you don't have really a nice way to write things down. Okay, so then let me do now the flexibility for magnetic flows. And then we will look at the case where your manifold is the two-torus. Okay, so which are the metrics we want to take? So T2, I imagine this as T with a coordinate X times T with a coordinate Y. And then we consider metrics which basically are just dependent on X in some way. Consider G, which is conformal to the standard flat metric, but the conformal factor just depends on X, and then I just write it as 1 plus AX. Okay, so where I write this in this way because I want to make some normalization. And so if I write it like this, I can make the normalization that AX has 0 average. Otherwise, it's just a conformal factor which just depends on X. And then my magnetic form sigma will also be just depending on X by function F, and then you have the area form. And also here you want to make some normalization that fixes this up to scaling. And the normalization that you can make here is just to ask that f of x times 1 plus ax dx is fixed and equal to. It is as basically it's a relative cousin of the integral of sigma. That's why it's natural to make this normalization. Okay, then if you do these two things, you can identify G sigma with a pair AB, which will be a pair of C infinity function with 0 average on the two-torus. So this is 0 average, 0 average, where the function P is obtained by basically taking a primitive of these two forms at the universal cover. So the function B is defined where B is defined as the derivative of B with respect to X is 1 plus A F minus 1. Okay, so this property tells you that this function here has 0 average. So then you can find the function B whose derivative is this function here. So this is just for convenience because now we want to apply also the implicit function theorem to find Zoll systems, and then it's nice to have a Zoll system which corresponds to the pair 0, 0. So then you know that for A B equal to 0, 0, you have magnetic geodesics are Zoll. For all energies. Okay, and then I am going to explore now in this class of systems where I found Zoll ones. A remark: if we just forget, if we just fix A equal to 0, we just look at examples which are basically flat, and we just move this. The construction will be very explicit, and this was done even before by Asselle and myself. These are a bit examples similar to the ones found by Zoll, where everything is kind of explicit. While in our case, since we are looking at non-flat things, we will really need the implicit function theorem. All right, so let me then state the theorem, and then I will quickly go and see what are the ideas of the proof. So in the Guillemin's case, there are these odd functions popping up, and here I want a similar class of deformations. Let's see. So I want to define what are odd functions in this case. To do so, let me kind of comment on how we can find odd functions in this case from a variational point of view. Let's say this is done using the radon transform. Maybe I want to do this here. So here the observation is that odd functions are equal to the kernel of the radon transform. What is the radon transform? It takes a function on S2 and gives me a function on S2. what I do, I take function u, apply the Radon transform, and then I need to give you a function on S2. So I need to tell you what is the value on a point Q on S2. And the idea is that you integrate the function u over a grid circle. So this is your point Q. Then you always have a grid circle lying at the equator of Q. You just integrate the function u over this. No? So it's equal to integral over CQ of u with respect to the length element of GC. Okay, so you integrate u in over grid circles, and then the kernel of this this map are exactly the odd functions. And here you can think why this function is relevant in this case is because the length is kind of finding critical points of the length give you the geodesics, and therefore if you now kind of differentiate the length function with respect to tau, then this is kind of the derivative that you will find. So in some sense, the Radon transform is the linearization of the action functional. And since action functional give you the closed orbits, if you want to have a lot of closed orbits, then you want that this linearization here is 0, because then you want that all orbits are closed. And that's why this condition here comes into finding the kind of tangent space, the space of Zoll matrix. And here we want to do something similar. In our case, magnetic systems are not given anymore by extremizing, magnetic geodesics are not given anymore by extremizing length, by extremizing some more general Hamiltonian action functional. So what you do, you define the analog operator for this functional, and you want to look at the kernel of this operator. So now what I'm doing is just put formulas to this principle here, and then we can say we define this magnetic Radon transform, which depends on H, the energy. So let's say from H, okay, 0. Next, RH. And now the input of my RH will be the tangent space of this AB. So this will start from functions with average 0, and then we spit out the function with average 0. And so this is the linear operator. Given by RH, then I plug in two functions, and I need to find a function as output. So I want to evaluate this at a point x, and this would be the integral over circle of radius 1 over square root of 2h, center x0, alpha, and then the length element minus integral over the disk, same radius, and that area. Okay, so imagine your torus, you take a point of coordinate x0, you take this circle of radius 1 over square root of 2h, and then you are integrating the first term over the boundary and then over the interior. Why this circle here? Because we saw that these are exactly the solutions of the magnetic geodesics in the unperturbed case. So these are just circles of a given radius. And then if you do if you look what is the Hamiltonian action in this case, you will see that it's exactly length minus area. And therefore, if you linearize, you arrive at this kind of operator, which substitute the Radon transform in this case. All right, so this is the operator now appears in the theorem. So the main theorem. Luca and with Massimiliano Berti. Tells me that for all positive energies, I can find a perturbation A tau, B tau, which is of the form tau alpha plus high order terms, and tau beta plus high order terms, such that magnetic geodesics are Zoll at energy H, if and only if this alpha beta belongs to the kernel of the linearized operator. Okay, so now this for each H, I will find a different deformation possibly, because everything here, this operator depends strongly on H. So now this is Zoll, but at a given energy H, which you think is fixed, and then for each H, you will find a different deformation possible. Is there any question about this statement? Theorem. Okay, so now in the remaining time, I want to give a sketch of the proof, which is kind of inspired heavily by Guillemin's approach. And also, what I forgot to say, that recently there was a generalization of Guillemin by Ambrosio, Codamarques, and Neves, which basically reproved Guillemin's result, but also did the case of these hypersurfaces of prescribed mean curvature. So they have also a notion of Zoll metric if you look at these hypersurfaces, and then their idea is really generalizing this approach of Guillemin using the implicit function theorem. But also as a particular case, they recover his theorem. So I think we also owe very much to these people. Okay, so then I want to just say something about the sketch of proof. Okay, so the technique is that we want to use the implicit function theorem. So what we want to do, we want to construct some function AH some nonlinear version of our Radon transform, such that we have a pair AB, which is a zero of this function, if and only if AB is Zoll at energy H. And if the Radon transform was the linearized version of the action, this would be actually the action of a suitable family of closed curve. So what is the idea is that now AH, AB will be five-dimensional reduction of the Hamiltonian action. Of AB at energy H. And then the idea is that if AHAB is equal to 0, this means for theory that this is constant. And then I know that all points are critical for the action. which mean by the least action principle that all now orbits are closed. Okay, and then the way you define this finite dimensional reduction is that really it picks up all the possible closed orbits. Also, these are really if and only, if. Also, you want to find now how to define this AH in a nice way, and then the geometry of the problem will help us, together with the fact that we are using systems which have an integral of motion. So how are we going to define this? Let me see. Okay, so first thing, I know that there exists a constant of motion. Let's call it taking values in the unit circle. So the idea is that these systems I presented just now, they have a symmetry with respect to shift in the y direction, because the x is the only variable appearing. And now the shift in the y direction in these symplectic manifolds is a symplectic flow, so it's not a Hamiltonian, but still it gives you something which is, it has values, multi-valued, but then it has values in the unit circle. So now if I take magnetic geodesic, for the pair AB, I can just look at those which have energy h and integral of motion I. We have coordinates, and then the velocity will be speed times an angle with respect to the x-axis. Okay, and if AB is actually close to 0, 0, then this angle here will always be increasing, and so we get the GSS. And so we get global surface of section. Surface of section, which is given by phi equal to some fixed value. If you have your torus here, this means that in the kind of energy surface, we have the two-dimensional surface given by all vectors which are tangent, which are in the same direction as x. And now if I have an orbit starting here, I'll arrive somewhere else on my surface of section, and then I can close the orbit just by going with x fixed and just going connecting with y. This I want to call it still Q A B I H. And now we'll take the Hamiltonian action of this orbit. A H A B, and now this is a function of an element in S1, and this element in S1 is actually the integral of motion. This is the action. Q A B. All right, so this is kind of the definition of the function.
Can you explain again what is the global section?
Yes. So now here we are looking at fixed energy. So you have in your energy surface, this is h equal to h. So above each point, this is kind of a circle with a given given radius. Now this is just parameterized by this thing. No? So it has reduced this, and the angle here parameterized the circle. And now I know that if AB is close to 0, 0, all my orbits will kind of rotate counterclockwise. So it means that if you start tangent to x, then the tangent vector will start rotating until it will be again tangent to the x direction. And so the surface of section is kind of you can think of this as inside h equal to h, and this would be a two-torus for each point. So it projects on the whole two-torus, and then for each point in the below, it's just a horizontal direction.
Oh, I see.
Yeah, so this is kind of the systems are never kind of contact type. You know, they have this closed global surface of section. Actually, there are suspension flows if you want to write down Hamiltonian description. So this first return map will be the Hamiltonian diffeomorphism of the two torus. Okay, yeah, thank you. There are other questions or comments? Okay, so right. I think I have much time.
I think you can have 5 more minutes.
5 more minutes. Okay, yeah, then I can just give some more details about the proof. All right, so now I have this, I've defined the action. I want to use implicit function theorem. Okay, for that, I can just maybe briefly write down the formula that one finds. Is, the whole formula is not important, but just one part of it that I'm going to now stress is 1 plus a x h phi x h phi times. And so it's kind of an integral formula where you integrate now over this angle phi, and this x is just the x coordinate of your trajectory, which depends on a, b, I, and h. This a is the a appearing here. Also, the thing that is important in this formula is that it causes a lot of troubles, is that now you have terms like this, where a is also it's both outside and inside the composition. So when I now want to differentiate in A, I will have troubles because I will kind of lose regularity when I try to see what is the differential of this thing, because now A appears also inside another thing that depends on it. But let me just comment on this in a second. So then you have your expression, then you can extend this to subwhole spaces. Then you have regularity R, and then it gets improved by 1/2. And the differential, the first thing is that the differential of this thing at the origin is exactly this operator we looked at before. And this is a short computation, is a surjective operator. So this is good news for implicit function theorem.
So what's the regularity of A as a function from HR into HR plus 1?
The regularity, right? It's not even C1, because now if I differentiate, then I start losing one derivative.
But you said it's good news for implicit functions.
Right, yeah, but this is like really, okay, like very, very small news, because now the next sentence is bad news for implicit functions. Okay, you already did spot me then. Yes. Okay. Then but issue one, yeah, this thing is not C1 because if I now do the differential at a nearby point, then if I want this to go from the same spaces, then I need to have higher regularity on AD. Only if AB are one regularity. And the reason is exactly that term over there. If I differentiate that term with respect to A, let me be a bit sloppy. You have a term of this type, then you have alpha x AB, and then you have A prime x AB, and then you have the alpha of x. Also, you see here, this requires loses one derivative. Okay, so if you want to go from the same spaces, then you need to pay one price here. And for this kind of the general fix to do this, fix one, is to use the Nash-Moser implicit function theorem. Also that you can, in some sense, work where your data is losing regularity, but in some sense, kind of in the implicit function theorem algorithm, it builds in the fact that you kind of regularize as you apply the iteration scheme. But so this kind of takes care of this. But the problem is that even if you kind of imagine to take care of this thing, these maps are not close to each other if A and B are close to each other. So this is the second problem. I think I will end here. Now, if you try to see what is the difference between the differential in AB and in 0, 0, you will see that this is not close. So issue 2, BAH, AB, and AH 0, 0 are not close to each other. Also, the idea is that if I now take something of that type, alpha x AB minus alpha x 0, 0, and I want to estimate this difference, then by the mean value theorem, I will also get some derivatives here. The problem is that also here you lose one derivative. Also, then it's not clear if you can apply the implicit function theorem because you would need this thing to be surjective in a neighborhood, not just at the point. The only information that you have is that this is surjective, but then you cannot just say that this is surjective because it's close to this one, because it's actually not true, because here you would need to go one regularity up even in the alpha. So, and for this you cannot do anything kind of coming from the implicit function theorem abstract side, in some sense. And for this, let me just finish with the second fix, is to look at so-called normal operator. Instead of looking at this one, you look at AH, AD, BAH, AD star, where this is the L2 adjoint. This is better behaved. This is now as highest order plus lower orders. And now this composition problem that you see here appears only on the lower order. Composition appear over here. only here. And so this tells you that basically now this B could be continuous. Now it's continuous. In AB, and allows you to invert, allows you to show that the HAB is surjective in a neighborhood. In that neighborhood. Okay, so in principle, I think it's not true that it's C1, but as soon as you do this kind of regularization with the normal operator, then things become better because basically these problems kind of get shifted to a lower order, and then this is enough to make the right estimates to get that still these operators are close to each other, and therefore you can use now this operator to write right inverse for this one and show the surjectivity. Okay, I think I'll stop here. Thank you.
So what can you expect in other dimension? This is Zoll business.
Yeah, so in another dimension, I think there is not even results for the Zoll geodesic flows. I think it's hard to maybe find. I think this linearization, even the linearization might be problematic because it's not surjective. These random transform, I'm not sure. Because what Ambrosio, Codamarques, Neves, they do the same thing, but with these hypersurfaces. So it seems that also for them, it's always codimension 1. Yeah, but I don't even know the linearized case, which would be the first place to start to see if you have at least linearized operator, which is surjective. Yeah. Yeah,
so you think you profit in low dimensions from the fact that there's not so much room? That the things are standing on each other's feet.
Yes, I think it's the right dimension also in the, because here this action function is a function on the space of this closed on a space of closed loops, and I think this has the right dimension to compare with the dimension to start with. If you go to higher dimension, that maybe it might have higher dimension than what the space of the data you're starting with. Yeah.
How do you know it's Zoll and not best what you got?
In this case here, you know, because it's perturbation of it's a perturbation of this sample. So basically, before what I drew was something like this. And now, if you know, if this closes up, it can just be closing up after one turn. And so this thing that closes up after one turn that already tells you that basically you have a nice foliation and it's not best. It cannot be best because basically the rotation number of the curve tells you that they all kind of close up after going around once. And it's not possible that they close up after going around more than one time, because then here you will get a shift either up or down. So if you don't close up at the first time, then if I repeat this thing, I will start drifting up. So it can never be close after, I don't know, going around multiple times. There is also more topological reasons. For instance, in this case, you cannot have a kind of better classification of Seifert vibrations on T3, which is the hypersurface that you're getting. You cannot have any kind of Seifert vibration of Besse type. And this is true also for higher genus surfaces. In the case of S2, there is actually an example which is Besse, but at one energy level, because you can do this thing of conjugating with the standard ellipsoid. So in this case, you find an example which is best, but it's much easier because then actually in this guise it's just the standard ellipsoid, right? It's a different construction, but it's more direct, let's say.
Any more questions? Well, if not, let's make Gabriele again.